Well, good morning to everyone. My name is Valk, and today I will present some of the results of my master degree. The title of this seminar is Analysis of the Orbital Anisotropy of Populations of Galaxies in Clusters. Well, galaxies are structures composed by stars, gas, dust, and dark matter. In the left figure, we can see the visible components of a galaxy, stars, gas, and dust. And in the right image, we have an illustration of the dark matter halo, where the visible components of the galaxy are in blue. When we look to galaxies, we can see that some galaxies present ionized gas and some galaxies don't present ionized gas. In the case when the galaxy have ionized gas, this gas can be ionized by young stars, by AGN. We can also have galaxies where we have AGN plus young stars, and in this case, we call these galaxies these transition galaxies. We also have hot low mass evolved stars ionizing the gas, and in galaxies where we don't have emissions line, we call these galaxies as passive galaxies. In this figure here, we have an example of AGN galaxies. And in the right figure, we have the example of the diagnostic diagram 1 that we use to identify how is the main ionizing source, responsible for the ionization of the gas in the galaxy. Another interesting fact about galaxies is that the properties of galaxies depend on their environments. For example, in the file we have generate spirals and irregular galaxies, and in high density environments like groups and clusters, we have much more ellipticals and lenticular galaxies. And in high density environments, the galaxies presents less gas content, lower star formation rate, and are more redder than similar galaxies in the defined region. And to explain this dependence between properties of the galaxies and the density of the environment, several processes are being proposed in the literature. We can see galaxy harassment, mergers, galaxy cannibalism, home pressure stripping, and starvation. In these two figures, we have an example of a galaxy experimenting home pressure stripping in the left, and a merger between galaxies in the right figure. One way to understand the relative efficiency of these mechanisms is analyzing the dynamics of the galaxies in high-density environments. And I did this in my master, and basically we use two equations, the spherical Gaussian equations, and these equations here that connect the observable profiles of the velocity dispersion, sigma p, and the numerical density profile, the projected numerical density profile, the E profile. Here, the beta is the velocity anisotropy parameter, and here is very important because giving us insights about the orbits of the galaxies. If beta is equal to 0, we have isotropic orbits. If beta is close to the unit, we have radial orbits. And if beta tends to minus infinity, we have tangential orbits. Here's a summary of the methodology that we used. We use the sample from the Carvalho et al. 2017, where we have 143 clusters and 11,195 galaxies. We classify these galaxies in 4 categories based on the main source responsible for the ionization of the gas in star forming, AGN, transition, and quiescent populations. We normalize the projected distance and the velocities of each galaxies to put all the galaxies together to create pseudo clusters that we call ensemble clusters. We estimate the observable profiles of the E profile and sigma P profile. We fit analytical functions to these profiles, these functional forms here. We execute the Mampos code to get the mass profile of the ensemble clusters and the beta profile of each populations. And we also use the inversion of the Dean's equations following the method of Solans and Salvador Soler to get the beta profile of a non-parametric weight. Here is the number of galaxies classified in each category and the distribution of the galaxies in the BPT, in the upper panels, and the one diagrams in the bottom panel. Here is the projected numerical density profile of each populations and the analytical fits that we obtain in the black line for each populations. The scalar radius of the profile, is RB, giving us information about how is the scattering of each population in the clusters. Because of this, we can see that the galaxies of the quiescent population have the smaller typical distance because we have a smaller values of the scalar radius, while star-forming galaxies have the bigger typical distance. The transition galaxies is slightly more concentrated than star-forming galaxies, and AGN galaxies have intermediate distance between quiescent and star-forming and transition galaxies. Here is the velocity anisotropy profile that we obtain for each population, and again, we have the quiescent population with the smaller velocity dispersion and star-forming population with the bigger velocity dispersion. And in this case, the AGN and transition populations have intermediate values of the velocity dispersion between the quiescent and star-forming population. Here is the beta profile that we obtain for each population. The solution of the Mampos is the solid color line in this box here, and the solution of the inversion of this equation is the dashed black line. And in this figure here, we have the velocity dispersion profile that we recover using this beta profile here. Basically, analyzing these two figures, we can see that the quiescent populations have a solution that is compatible with the Mampos solution, and we also have a comparable, we also have an equilibrium solution for the AGN population obtained using the Mampos code. But for the star-forming population, the solution that we obtained is incompatible with the Mampos solution. And for the transition populations, we have a solution that is approximately comparable with the Mampos solution. The main conclusions that we obtained is that are that the quiescent galaxies are in a more advanced state of realizations because the lower typical, the smaller typical distance and the lower velocity dispersions, and we also get an equilibrium solution using the Mampos for this population. And the star-forming population shows the clear signals of non-equilibrium because we have the bigger typical distance for these galaxies, the bigger velocity dispersion, and we don't find an equilibrium solution using the Mampos for this population. Galaxies from the T populations exhibit a higher degree of virialization when compared to the star-forming galaxies, and we obtain equilibrium solution for the AGN populations, but we have a small number of tracers, galaxies, in these populations, and because of this, the uncertainties in this profile, in their profile, are very high, and is difficult to draw strong conclusions. Thank you for attention.